Hello, beloved physics class. I am sorry I could not be there today. However, this short video hopefully will serve as some kind of a substitute for having a real teacher in the class. Today we're going to start looking at our very last subject in the field of mechanics. That's what we've been studying all along, by the way, is something called mechanics, the study of how things move and why things move. And our last topic in mechanics is this idea of work, which is important because it leads to concepts later on of energy. And we'll explore that relationship also. Work is a deep concept in physics because it is not only important in mechanics, but also in the areas of electricity and magnetism, high energy and particle physics. Particle physics. It's also important in things like gas laws, work that gases do. It's important in quantum mechanics, the idea of work is. So it's a deep concept that pervades all of physics. But in every case, the fundamental importance of work is that it gives us ideas about the energy of a system. So, what is work? What is work? Fundamentally, work is something done on an object by a force. So, work is done by forces on objects. For example, if we look at the forces on the apple here, of course you see a gravity force and you see a normal force. And if the person lifts the apple straight up, each of those forces might have the opportunity to do work on the apple. In this case, the normal force does positive work, and the gravity force does negative work. Notice the normal force is aligned with the distance moved, whereas the gravity force is anti-aligned. And that's why the normal force does positive work. It has to do with the alignment of the normal force and the distance traveled. This is the key idea about work. It's about the alignment of the force with the distance. Now, if the man should start moving, say, to the right, and he does not lift the apple up or down, now the distance is directed this way, but the normal force and gravity force, of course, maintain their same alignment. So now we have a distance to the right, but a normal force upward. And in this case, the normal force does no work at all, zero work on the apple. Notice now that there's no alignment. The normal force goes up and down, the distance goes right and left. We have a 90-degree angle, and in this case, the normal force has no alignment with the distance, so therefore zero work. The same could be said of the gravity force. Since the gravity force goes straight down, and the distance is still sideways, again, there's no alignment at all with the gravity force and the distance, and so going sideways, both the gravity force and the normal force do zero work. Now, suppose that the man lowers the apple. He has stopped moving and he begins to lower the apple. At this point, the apple's not going up, the apple's going down. And now the distance is directed downward. Guess what? The gravity force is now doing positive work, and the normal force is now doing negative work. Negative work. Positive work. Because now the gravity force is aligned with the distance on the way down, and G and D both going in the same direction, and the opposite is true of the normal force. So we have seen that work depends on two things. It depends on the force, how strong the force is. It depends on the distance, how far the object travels. But then it also depends on something to do with the alignment of those two things. We have seen that when they're aligned, it's positive. When they're anti-aligned, it's negative. And when it's perpendicular, when the force is perpendicular to the distance, we have zero work. What happens when we have a situation like the one below, where we have a force and a distance that are, a tension force and a distance that are somewhat aligned? They're somewhat in the same direction. Well, here, the idea is we want to only include the part of the tension force that is aligned with the distance. So we can break up that tension force into two parts. A part that goes this way and a part that goes that way. Those two red vectors are equivalent, if we add them up, to the blue vector. And if this angle is theta, the angle between our tension vector and our force vector, then this one here that is perfectly aligned must be t cos theta. And so the work done by the tension force here on the block would be the force, T, times the distance, D, times the cosine of the angle in between them, which will control the alignment between T and D. And general terms, though, if this is a tension force here, probably it's better to just say the force times the distance times the cosine of the angle in between. So the equation for calculating work is the one in the red box here. And this will handle all of our work issues for a time to come. Notice the cosine function works in this case, but it also works very nicely for the case when you're perpendicular. Or if the distance is this way and say the normal force is that way, we know that the work done here is 0. But what is the cosine of 90 degrees? Every schoolgirl knows cos 90 equals 0. So if we apply this equation to this situation, you can see whatever the force is and whatever the distance is, it kind of doesn't matter, because when we put in the cosine of 90 degrees, we get 0. Similarly, the cosine function works very nicely when the distance is, say, this way, distance, and the force is that way, force. And now there's 180 degrees between force and distance. And the nice thing here is cos of 180 is equal to -1. And that explains why we get our negative values for force when we're for work when we're anti-aligned. And of course, the ideal case is, I suppose, when the force and the distance are perfectly aligned. Now we've got 0 degrees between them, and cos of 0 is 1, positive 1. So we've got the special case of anti-aligned, explained nicely by cosine. We've got the special case of perpendicular, explained nicely by cosine. We've got the special case of alignment, handled perfectly by cosine. And then cosine works for everything in between. So let's take a look at this equation now. Capital W is the symbol used for work. The standard units of force are, well, if it's MA, that would be M is kilograms and A is meters per second squared. So those are force units. The standard unit for distance, meters. Cosine is the ratio between two sides. So if it's a ratio between two lengths, the lengths cancel. If it's a ratio between two velocities, the velocities cancel. Cosine is unitless, so we don't have to write anything for the units of cosine. And so the units of work turn out to be kilograms times meters, that's meters squared, divided by seconds squared. That mouthful of units is abbreviated in the same way we abbreviated this as newtons. This gets named after a scientist who did a lot of, oh, here comes a pun. He did a lot of work with work and energy, and he found the person who it's named after is James Prescott Joule, who was a scientist, a British scientist in the 1800s, who did a lot of put a lot of effort into figuring out the nature of work and heat energy. And in his honor, the unit of work is named after him, the joule, abbreviated with a capital J since it's a person's last name. So we will always be expressing all of our answers for work in joules, capital J.